Welcome. So today we'll be starting a new subject in discrete math. It's called combinatorics. Now, what is combinatorics? So basically combinatorics is a branch of math concerning studies of finite or countable discrete structures. Aspects of combinatorics include counting the structures of a given kind and size, deciding whether certain criteria can be met, and constructing and analyzing objects meeting the criteria. Finding largest, smallest or optimal objects, and studying combinatorial structures arising in an algebraic context or applying algebraic techniques to combinatorial problems. Now this is what Wikipedia says about combinatorics. And as you can see in this quotation, there are sub-branches of combinatorics, for example, enumerative combinatorics, combinatorial design and matroid theory, extremal combinatorics and combinatorial optimization, algebraic combinatorics, and so on. This is one of the most interesting and challenging part of discrete math, and we will see some of the basic steps or basic aspects of combinatorics. Of course, we will not be able to do a full in-depth coverage of combinatorics. In fact, each of this subject itself requires a whole course, full advanced course for understanding or even understanding the context of this subject. Now, why do we need combinatorics? And again, as Wikipedia says, combinatorial problems arise in many areas of pure mathematics, notably in algebra, probability theory, topology and geometry, and combinatorics also has many applications in mathematical optimization, computer science, ergodic theory, and statistical physics. Many combinatorial questions have historically been considered in isolation, given an ad hoc solution to a problem arising in some mathematical context. Combinatorics is used frequently in computer science to obtain formulas and estimates in the analysis of algorithms. So in short, combinatorics is kind of the backbone of mathematics or applied mathematics or many fields of mathematics actually. So in the next few weeks, we will be concentrating only on this subject of combinatorics, and let's see how to go about it. So in short, combinatorics is a branch of subjects that involves counting. So in fact, that is what we will be doing for most of our time in combinatorics. We will not have time to delve into the other aspects of combinatorics, but we will be talking about counting. Now, a typical question is something like, I give you a set and I ask you the cardinality of set S. Now, what is cardinality? Cardinality means the number of elements in this set S. Now, you might be wondering what is there to ask in this question. If I give you a set, you just count the number of elements in set S. Unfortunately, sometimes the set S is not given you explicitly. It is given you kind of implicitly. In other words, something like, okay, take all the solutions satisfying this form. This is a set. Right? And it is not a set that I have given you explicitly. And now I ask you what is the cardinality of set S? Right? Now, the main question is, how is this set given? As I told you that if the set is given explicitly, meaning set S is, say if I say that, oh, the set S is the set of 1, 2, 4, 6, 9, 10. Now you can just go and count it and say, oh, the set has 6 elements. But what happens if I tell you the set S is the set of prime numbers less than 3000? Now, okay, already you can realize that counting this set is not the easiest job, and you don't know how to exactly simplify your way, get a simple solution other than just listing out all the possible prime numbers. Now, in general, we can ask you something like, okay, what is if S is the set of all prime numbers less than the integer n, then what is the cardinality of the set S? So that means I am asking the number of prime numbers less than n. Can you give me a formula for that? And again, you can understand that this is a very hard problem. It's not a trivial problem. It's not just counting the number of primes. So, as I just told here, the sets are usually described in words, like I just now did. And so a typical example is how many elements of a set satisfy a certain set of conditions, right? So in the other example, if the universe that we are looking at is the set of integers, I am asking how many integers satisfy the condition that it is less than n and it is prime. And that is what we want to ask. Okay? Equivalently, the same question can be phrased in a different way. How many ways can you draw an element from the set such that the element satisfies the set of conditions? So these are two exactly same things. I mean, the first one says that, okay, how many elements are there? Second one says that if I am asked you to draw a particular number, say between 1 to n, such that the number is prime, how many different ways can you draw it? And of course, the number of ways you can draw it is number of prime numbers less than n that is there. So you can understand that these two numbers are exactly same, these two questions, and we would be kind of jumping between the first way of stating it and the second way of stating it. So let's look at some examples. So here are some examples. First one is, how many n-digit numbers in decimal are there where no consecutive digits are same? For example, something like if n equals to 1, n1 is a trivial number. If n equals to 2, then what I am asking is that, okay, you can have 1, you cannot have 1, 1, but you can have 1, 2, you can have 1, 3, you can have 1, 4, you can have 1, 9, you can have 2, 1, you cannot have 2, 2, but you can have 2, 3, you can have 2, 4, you can have 2, 9, and similarly it goes on. Now, of course, if n equals to 2, you can almost write down the actual number, right? Or actual number of such options. But if n is a general parameter, then how many n-digit integers are there where there are no two consecutive digits, right? So, I mean, no consecutive digits meaning like 3, 4, 4, 5, 8, 9 is not has two consecutive digits same because there are 4 followed by a 4. But for example, 3, 4, 5, 4, 8, 9 is fine. This is an integer with 6 digits where no two consecutive digits are same, because 3 is followed by 4, 4 is followed by 5, 5 is followed by 4, 4 is followed by 8, 8 is followed by 9. No integer, so there's no two digits next to each other that are same. Right? So this is a problem. We will be getting back to this set of problems after we do some theory on this particular subject of combinatorics. But let me first explain you all the various problems that we have, or some of the problems that we have. The next one is, consider functions from the set 1 to n to set 1 to k. The 1, 2, 3, 4 to n to 1, 2, 3, 4 to k. How many non-decreasing functions are there? Now what do I mean by non-decreasing function? Meaning if I take x and y from this set 1 to n, and if x is less than y, then fx must also be less than or equal to 1. And it should not go down. Right? So in some sense, if I end up plotting this graph, so this is f of x. Of course, it has integer values it takes, right? And if this is the x. Now x's. So of course it will be a kind of a dot, correct? So maybe f of 1 is 1, f of 2 is 3, f of 3 is 4, and so on. But if I draw this one, it should not end up suddenly dropping off. It is fine if it remains in the same level. For example, this one. Yeah, something like this is okay, where there is the function curve doesn't go down. The function curve is allowed to remain horizontal to the x-axis. How many functions are there from 1 to n to 1 to k? The third question is, if you have n identical toffees and you have k kids, how many ways can you give it to the k kids? So for example, if I have 5 toffees and 2 kids, how many ways can I give it? I can give first kid, I can give 3, I can give 2 to the other one. Or I can give the first kid 2, 3 to the other one. Or I can give 1 and 4 to the other one. Or I can give 4 and 1 to the other one. Or I also can give 0 and 5, 5 and 0. So here, for example, you can see that there are 6 ways of giving this 5 toffees to these 2 kids. Right? Now, how many ways, if I have a general n number of toffees, k kids, how many ways can I distribute the n toffees to k kids? Again, we will go over this problem after we do some theory on this subject. The last one that we are looking at is, look at the strings of length n made by zeros and ones. How many of them are there such that there is no consecutive zeros? Meaning, if I have a string 1 1 0 1 0 1 0 1 1 is fine. This is an accepted string. But something like 1 1 0 0 0 1 1 1 is not an accepted string because there are 2 consecutive zeros. Or here actually there are 3 consecutive zeros. So how many strings are there of length n which doesn't have any consecutive zero? Right? Now this is the 4 problems, and let's try to take a step back and see some theory behind this subject of combinatorics, and we will get back to these problems after a couple of videos. Now, How to count? Now this is an important question. Note that each problem is unique and has to be solved by applying a technique that fits it. Now which technique fits which problem is not known as per se. In fact, counting is one of the most challenging subjects in mathematics. I mean, some of the best minds have worked on it. In fact, some of the best works of Srinivasa Ramanujan was on counting. We will be talking briefly on this particular aspect in one of the videos. Now there are some handy tricks and tools to attack these problems, and that we will be learning in this set of lectures. But again, let me reiterate, these problems, every problem is unique and you should try to be creative in trying to solve any of the problems. The tricks and tools are just some handy gadgets that we'll have to attack this problem. Okay, so let's start with the simplest of tricks or rules that is there. The rule says that suppose P is the number of ways of choosing an object satisfying some set of conditions, say P, capital P, and small q is the number of ways of choosing an object satisfying the condition capital Q. And if there is no object satisfying both P and Q, then the number of objects that satisfy either the condition P or conditions Q is P plus Q. Right? So this is a very simple additive rule that we have. And we also have another rule called the product rule. And this says that if, say, we have to choose two objects, and if P is the number of ways of choosing an object satisfying P, and Q is the number of ways of choosing an object satisfying the condition Q, then the number of ways of choosing two elements such that the first element satisfies condition P and the second element satisfies the condition Q is P times Q. So let's quickly go over some examples to see both these rules. Say in a class there are 40 boys and 50 girls. How many ways can you pick a monitor from the class? Now here let me first define two conditions P and Q. P being the number of ways, or rather I should not say the number of ways, but P is the case that monitor is a boy. Q is the case that monitor is a girl. Now if this is the case, then what are you asking? In this problem we are asking how many ways can we pick up and monitor who either satisfies P, meaning the monitor is a boy, or satisfies Q, which is the monitor is a girl. Now number of ways I can pick a monitor who is a boy is, since there are 40 boys, I can pick any one of the 40 boys. That means this is 40. So in our definition P is 40. And here the Q is 50. Right? So this is, since there are 50 girls, number of ways I can pick up a monitor who is a girl is, I can pick any one of the 50 girls and I get 50. So the total number of ways I can pick a monitor who is either a boy or a girl is P plus Q, which is 9. Now you might think that this is a very stupid kind of example. I could have just straight away gone and proved it directly, that the number of ways of picking a monitor from 90 students is 90. You are right, it is just an example of for showing the additive rule. Now the additive rule is something really simple, but also we do apply it all the time, and we will be coming back to the additive rule sometimes next video, actually next to next video, when we will be seeing some more complicated examples for the additive rule. Now, let me ask the second question. How many ways can you pick a boy monitor and a girl monitor from the class? So, I want to pick two monitors. First of them will be a boy monitor, second one will be a girl monitor. Now again, the same way that I did the last time here, P is the monitor is a girl, monitor is a boy, and Q, the monitor is a girl. And there we saw that here P was equals to 40 and Q equals to 50. Now the number of ways I can pick first a boy monitor and then a girl monitor is by the product rule P times Q, which is 2000. 40 times 50 is 2000. So there is 2000 ways of picking one boy and one girl, such that one of them is a boy monitor, and one of them is a girl monitor, right? So this is some very simple application of the product rule and the addition rule. Now, using these two simple rules, let's move ahead and try to see some more interesting problems. So here is the problem set. Imagine you are a police officer and there are n constables in your police station. Now every night, for 7 nights, you have to assign one of the constables to stay awake at night. Now you can ask a constable to stay awake for more than one night. Maybe for example, one particular constable is a very is someone you depend on much more. So you want to ask him to stay awake on 2 of the nights, on Monday and Wednesday. Right? So let's think of this way, that there are the 7 nights, namely Monday, Tuesday, Wednesday, Thursday, Friday, Saturday and Sunday. Now each of the night you have to assign a constable, right? So I can, for example, I can put the here constable number 1 goes for Monday, constable number 2 goes for Tuesday, constable, maybe I can again ask constable 1 to take up do the duty again on Wednesday. Thursday, maybe I can ask constable number 3. On Friday, maybe I can again ask constable number 1. On Saturday, maybe constable number 2 I ask, and on Sunday also I ask constable number 2. Now this is a possibility, right? This is a one way of assigning the constables, constable 1, 2, 3 to the 7 days. Now there is another way I can do it, right? For example, I might have decided that, okay, no, I will put constable 3 here and constable 1 here. Now as you can see, there are different ways of filling up this chart. Question is that how many ways can you fix the schedule for who is staying awake at which night? And how many different charts can you prepare? Now the answer is not too hard. It's again by the kind of the same product rule application. On the first night, I can assign. How many ways can I assign a constable? I can assign any of the n constables, right? So the number of ways I can assign is n. On Tuesday, again the number of ways I can assign is n. I can ask any of the n constables again to stay awake at night. On Wednesday again n. And in fact for all the days, number of ways I can fill up that or assign as constable to that day is n. Now my product rule, the total number of ways in which I can assign constables to these days so that these are ordered in some sense, like there's an order way of going about it, is the product of them, which is n power 7, right? First day n, second day n. So number of ways I can put a constable in the first day and a constable in the second day is n times n, which is n square, and then along with Wednesday then cube and so on. Right? So this is a very simple observation, and in fact this falls under a general problem which basically asks the question: if there are n people in a group, how many ways can you choose r people? Repetition is allowed and ordering matters. Now let's try to see how does the earlier problem match here. Earlier problem I had n constable and there r was the 7. I have to choose 7 people in this way that I have to choose 7 constables for 7 days. Repetitions allowed in the sense that the same constable can be assigned multiple nights. And ordering matters, meaning whether constable 1 does the Monday job and constable 2 does the Tuesday job is different from constable 2 doing the Monday job and constable 1 doing the Tuesday job. So if I flip or if I shuffle the assignments, I get a completely different allocation, right? So again, how do you answer this question? Let's see. First of all, there are positions, right? We have to choose r people and their ordering matters. So let me call this one for position 1, position 2 till position r. Now position 1, number of ways I can fill up position 1 is I can choose any of the n people, so n. Number of ways I can choose position 2, again since I am allowed to reuse these people and the repetitions are allowed, we can choose it with n also. And similarly for all the r positions can be filled with all the r positions, each of them can be filled in n ways. So the number of ways I can fill up all of them is n times n all the way, which basically is n to the power r is the answer. Now this is also sometimes called choosing with replacement, because here what we are doing is that we are drawing a person from the list and then so in some sense imagine that you have n people and their names have been written into a piece of paper and put into a basket. Now what I can do is that I can pick up one person's name from that paper from the basket. I see someone's name assign that person the first position, then I put back the slip into the basket so that I can again have an option of picking that person up, right? And I can draw this one more cheat and assign the next one, next cheat to the next position. So this way we are basically choosing with replacement. We are replacing the cheat every time. So this is what is a very generic thing that we did, very general statement that we for what we just saw, the constable problem, right? Now let's look at some slightly different problem. Here it has the same thing, except that again you have to assign the n constables for 7 nights, but you cannot ask a constable to be away more than 1 night. Now let's try to see how to go about it. Again, I have Monday, Tuesday, Wednesday, Thursday, Friday, Saturday and Sunday. Now, how many ways can I ask? How many ways can I pick a person to serve the Monday night? Of course, all the n people are there, and hence I can pick up in n ways. Now, how many ways can I pick up a constable to serve the Tuesday night? Now, the person who has already done the Monday night cannot be asked, because I have been told that a constable cannot be asked to do 2 nights. So he is out of question. So I am left with n-1 possibilities, which means that on Tuesday I can fill up this position in n-1 ways. And what about Wednesday night? Wednesday night I cannot use the person who has served the Monday night. I cannot use the person who has served Tuesday night. So I am left with n-2 constable, and I can pick any one of them. So it is n-2. And it goes on like this. So I will have n-3 over here, n-4, n-5 and n-6. So at the end, how many ways can I select these 7 constables? I can n times n-1 times n-2 times n-3 times n-4 times n-5 times n-6 times that's all, n-6. So it's like the sum product of all of this is what my answer is. So again, this can be formed in a slightly more general setting. Namely, there are n people in a group, and how many ways you can choose r people with repetitions. Repetition is not allowed, but ordering matters. Meaning I have positions, I have the positions P1, P2 till PR. The first one I can assign in n ways. The second one I can assign in n-1 way. Third one in n-2 ways, just like the case of the constable problem. And the last one will be n-r+1 way. So the answer would be the product of this set, n times n-1, n-2 to n-r+1, which is by definition n factorial by n-r factorial. Right? Now note that here ordering matters in the sense that if I pick constable 1 here and constable 2 here and constable 3 here, constable R here, that is different from constable 1 2 here, 1 here, and 3 4 3 2 are here. So these two are two different ways of assigning people, because I'm assuming that these two things are distinct. I mean, these two positions are ordered, right? So P1 and P2 should not be mixed with each other. And as you can expect, since I am not allowing repetitions, this is also called the choosing without replacement. Now this is also a special case. There is a special case of this. Namely, if I give you n people in a group and ask them to arrange in an order, where order matters. So in that case, what am I asking? I am asking that can you choose n people from n? Can you choose n people from this n? How many ways can you choose n people from this group of n people? So the first one can be, I can pick any one of the n people. Second one, I can pick any one of the rest of them, and it goes on till I have no one left to pick. So this one is, so R here is n, and if you plug the values of R in the earlier problem, you get n factorial. So thus you see that this n factorial is in fact the number of ways in which n people in a group can be arranged in a n factorial is the number of ways in which you can order n people in a particular order. I mean, where order matters. Now, before I go to the next problem, let's do another nice rule. We call it equivalent partition rule. Now let S be a set, and let us have this the three bars be an equivalent relation on the elements. Now once you have the equivalent relation, you know that I have equivalent classes. It's all the set of elements that are equivalent to each other. Now if all the equivalent classes has the same size, namely R, then the number of equivalent classes that we have is sized by R. Now this is not a very hard thing to realize, right? I mean, if I have a set here and I have equivalent classes, all of them have size R, then total number of this kind of same equivalent classes is that S by R, right? So we can use this one for counting certain cases. For example, look at this problem. There are n constables in our police station. You have to pick 7 of them for a project. How many ways can you pick your team? Now the difference from this and the earlier one was that here the ordering doesn't matter. I don't care about who is the leader of the team and all. There are 7 people in the team. How many ways can you pick them up? Right? Now, okay, maybe what we do is the following. Let's first write down the thing that we have done, which is these 7 days of the week. And let's first try to assign the various constables for these 7 days. So let's imagine that I have so I have assigned constable 1 here, constable 2 here, constable 4 here, constable 3 here, constable 6 here, constable 9 here and constable 10 here. Right? So this is one way of doing it. Now this is one way of, in the earlier problem, assigning the 7 constables to 7 knights. But then in that problem, even this one was a different way of assigning constables. What I have all done is that I have swapped these constables for Monday and Tuesday. Note that in the earlier problem, they two were different. But in this problem, when I don't care about ordering, I don't care about who is doing which day, I just want 7 people, these two are equivalent. So now, because here I picked the same set of people. So in fact, question is that if I give you a set of 7 constables, as long as this set has the same set of constables, they are equivalent. Question is that how many such arrangement is equivalent to, say, this particular set? It is the same number of ways I can permute these 7 constables, right? So this is equivalent to 7 factorial number of other picking ups. So in the whole set, which if you remember was n minus, it was n factorial by 7 factorial it was n factorial by n minus 7 factorial. This was the total number of ways in which I could pick 7 people, 7 constables for the 7 knights by ordering matter. But now each of those arrangements has an is equivalent to 7 factorial number of ways. So by the equivalent partition rule, to get the number of groups that I can get, which is in the case that I have to look at the number of equivalent classes, is that I have to divide this number by 7 factorial and hence I get this number. Right? So you might have seen this particular thing earlier. This is called n to 7, of course. Number of ways I can choose 7 people for n, a group of n people. But the idea is basically this, that you first see how many ways you can pick the people in an ordered manner, and now each of the ordered selection is equivalent to 7 factorial number of them, and I have to divide by 7 factorial to get the number of equivalent classes. Again, in the general setting, same kind of idea. If I have n people in a group, and how many ways can I choose r people? Repetition is not allowed and ordering does not matter. It is whatever the answer that I had last time by r factorial. Right? It is exactly the same thing that we did for the constable case, which is n factorial by n minus r factorial and r factorial, which is n choose r. Good. So this is the number of ways in which we can choose when repetitions are not allowed but ordering does not matter. Now what happens if I ask this following question. There are n constables in your police station. You have to give the names of 7 constables. You can give a constable name more than once. How many ways can you give the 7 constables? So in other words, what I am asking is, let me go for the general problem here, that there are n people in a group. How many ways can you choose r people when the same person can be chosen a few number of times? Repetitions are allowed, but ordering does not matter. I don't care about the ordering inside each group. Now, how do you solve this particular problem? Okay, to solve this problem, let's first start with the positions like we did. But earlier we were writing the positions as P1 to PR. Unfortunately, we cannot write such things because the positions are not distinct in the sense that I don't care about the ordering. Since I don't care about the ordering, so I cannot write this P1 to PR. Instead, let me just try to write as some round balls. So there are round balls and I have two. And I have, how many of the round balls I have? I have R round balls. Right? And these are the positions that are there. Now, I have to kind of give the positions to people. So the people are marked, right? So I have the person 1, P1, or maybe I should write it as, say, I will use the fact that they are constables. So they have the constable 1, constable 2, till constable n. I have n constables. Now question is that how many times should constable 1's name be in the group? Should it be once, twice, or no times, or odd times, or what? So in other words, it is like I have these points, and if I draw a line, I kind of say that, okay, if I give the constable 1, 2 positions, then I will draw a line here. And it says, okay, everything left of the line is for constable 1. This basically implies that constable 1 gets 2 positions in that R, among the R positions. Similarly, maybe constable 2, I will draw a line here, and whatever the number of points that are there in constable 1 and constable 2's line, in this case 0, is the total number of positions that constable 2 gets. Or in other words, here constable 2 doesn't get any position. Right? So maybe constable 3, I will draw a line over here, and that is saying that constable 3 gets a position, 1 position. Maybe constable 4 has line next to constable 3, that is constable 4 does not get a position. Here constable 5 doesn't get a position. Here constable 6 gets 3 positions. So in other words, and at the end of the day, how many lines should I draw? If I have drawn n minus 1 such vertical lines, at the end I will say that, okay, whatever is left, it goes to constable n. So in other words, this is, so a particular arrangement of this round circles and straight lines indicate that since there are n minus 1 bars or straight lines, I have n intervals in between the straight lines, and that indicates the number of times the ith constable's name is in the group. So in other words, the number of ways you can permute or number of ways you can write down the set of a string forming with odd circles and n minus 1 red lines is going to be the number of ways you can pick r constables from n constables, where you draw it with repetition but ordering does not matter. Now if you do it, you see that how many objects are there. There are r circles and n minus 1 straight lines, right, which in turn becomes r plus n minus 1 objects are there. So the number of ways I can write a string with r circles and n minus 1 straight lines is r plus n minus 1 factorial. I just permute all of them. But since all the positions are identical, means since all these circles are identical, I should divide by r factorial, and I should also divide by n minus 1 factorial, because these bars are also identical. So this way I have been able to count in an indirect way how many ways I can select r people from n people, where repetitions are allowed and ordering does not matter. So the answer is in fact n plus r minus 1 factorial by n factorial times r minus 1 factorial, which do become n plus r minus 1 choose r minus 1. So this particular way of picking in this particular problem, the last one that we did, is reasonably complicated and tricky. We will come back to it again next video in a different light, and we will see the same problem in the next video also. So for now, what we have seen that if you have to select k objects from n objects, then the number of ways of doing it is, in the case of with repetition it is n factorial, when we do it without repetition and order import is n factorial by k factorial. Sorry, I have made a mistake here. This should be n factorial by n minus k factorial. This is n factorial by k times n minus k factorial, and the last one which we just did now is this one, n plus k minus 1 factorial by n minus 1 factorial times k factorial. In the next video we will come back and see some more counting problems. Thank you.